Students often seek a deeper understanding of the various concepts in physics. From classical mechanics to quantum theory, it offers insights that illuminate phenomena ranging from everyday occurrences to cosmic events. Study of physics not only enhances scientific literacy, but also fosters critical thinking, enabling students to explore the captivating interplay between matter, energy, and the fundamental laws governing our reality. So let us explore the world of physics now. Dear students, in this video, we are going to have an introduction about electromagnetic waves, Maxwell's displacement current, and his correction to Ampere's circuital law.
Chapter 5, Electromagnetic Waves. In this chapter, we are going to know about the displacement current, Maxwell's correction to Ampere's circuital law, Maxwell's equation in integral form, protection and properties of electromagnetic waves, Hertz experiment, sources of electromagnetic waves, and electromagnetic spectrum. Now let us see about this introduction of electromagnetic waves. So you would have seen a rainbow in the sky and also lightning, which contains visible spectrum only. This visible spectrum is part of electromagnetic spectrum. We see the world around us through light, and light from the sun is one of the sources of energy without which human beings cannot survive in this planet. Light plays a crucial role in understanding the structure and properties of various things from atom to universe. Without light, even our eyes cannot see the objects. So what is light? This puzzle made many physicists sleepless until the middle of the 19th century. Earlier, many scientists thought that optics and electromagnetism are two different branches of physics. But from the work of James Clerk Maxwell, we actually enlightened the concept of light from his theoretical prediction that light is an electromagnetic wave which moves with a speed of 3 × 10⁸ meters per second in free space or vacuum. Later it was confirmed that visible light is just only a small portion of electromagnetic spectrum, which ranges from gamma rays to radio waves. In the Unit 4, we studied that time-varying magnetic field produces an electric field, that is Faraday's law of electromagnetic induction. Maxwell strongly believed that nature must possess symmetry, and he asked the following question: when the time-varying magnetic field produces an electric field, why not the time-varying electric field produce a magnetic field? Just like symmetry observed in the case of a dragonfly, butterfly, and a leaf. And later he proved that it is indeed true. And in 1888, Heinrich Hertz experimentally verified Maxwell's prediction, and hence this understanding resulted in new technological invention, especially in wireless communication, laser, which is the abbreviation of light amplification by simulated emission of radiation technology, radar, the radio detection and ranging, etc. So this cell phone tower, the cell phone, X-ray radiograph, they are all based upon electromagnetic waves. So in today's digital world, the cell phones have greater influence in our daily life. It is a faster and more effective mode of transferring information from one place to another. It works on the basis that light is an electromagnetic wave. And in hospitals, the location of bone fracture can be detected using X-rays, which is also an electromagnetic wave. And in cooking also, we are using microwave oven, and the microwave is also an electromagnetic wave. There are plenty of applications of electromagnetic waves in engineering, medicine, like laser surgery, and defense, in radar signals, and also in fundamental scientific research. And in this unit, the basics of electromagnetic waves are discussed. The first case, let us study about the displacement current and Maxwell's correction to Ampere's circuital law. Now let us first consider what is induced magnetic field. Faraday's law of electromagnetic induction states that the change in magnetic field produces an electric field, and mathematically it is written as line integral E dot dO equal to minus d by dt of phi b, that's equal to minus d by dt of surface integral of b dot dA, as this involves area and this involves only the length. And here phi b is the magnetic flux and d by dt is the total derivative with respect to time. And this equation 5.1 means that the electric field E is induced along a closed loop by the changing magnetic flux phi b in the region encircled by the loop. From symmetry considerations, James Clerk Maxwell showed that the change in electric field also produces a magnetic field, and that is given by this equation. Line integral of b dot dl equal to minus d by dt of phi e, and that's equal to minus d by dt of surface integral of e dot dA. That's equation 5.2. Where this phi e is electric field, electric flux. And this is known as Maxwell's law of induction, which explains that the magnetic field B is induced along a closed loop by the changing electric flux phi E in the region encircled by that loop. This symmetry between electric and magnetic fields explains the existence of electromagnetic waves such as radio waves, gamma rays, and infrared rays, etc. Now let us see what is displacement current and Maxwell's correction to it. In order to understand how the changing electric field induces magnetic field, let us consider a situation of charging a parallel plate capacitor which contains non-conducting medium between the plates. Let a time-dependent current IC, called conduction current, be passed through the wire to charge the capacitor. Now, this Ampere's circuit law can be used to find the magnetic field produced around the current-carrying wire. To calculate the magnetic field at the point P near the wire and outside the capacitor, let us draw a circular Amperian loop which encloses the circular surface S1, that is given by 5.3 here. Amperian, this is the Amperian loop, and the conduction current IC is passing through it. So using Ampere's circuit law for this loop, we get this expression 5.3, that is surface integral b dot dl equal to mu naught IC, where this mu naught is called the permeability of free space. Now, this applying the Ampere's circuit law, the loop enclosing the surface S2. The same loop is enclosed by a balloon-shaped surface S2 such that boundaries of two surfaces S1 and S2 are the same, but the shape of the surfaces is different, like this. So as the Ampere's law applied for a given closed loop does not depend on the shape of the enclosing surface, the integrals should give the same answer, but by applying Ampere's circuit law for the surface S2, we get this expression surface integral of b dot dl equal to 0. The right hand side of the equation is 0 because the surface S2 nowhere touches the wire carrying conduction current, and further there is no current flowing between the plates of the capacitor. That's the gap between the plates. So the magnetic field at the point P is 0, hence there is an inconsistency between the equations 5.3 and 5.4. Maxwell resolved this inconsistency as follows. While the capacitor is being charged up, varying electric field is produced between the capacitor plates. There must be a current associated with the changing electric field between capacitor plates. And in other words, the time-varying electric field or time-varying electric flux produces a current. And this is known as displacement current flowing between the plates of the capacitor. So here we are applying the Gauss law between the plates of the capacitor. And from Gauss law of electrostatics, the electric flux between the plates of the capacitor is given by the expression phi E equal to surface integral of E dot dA, and that's equal to EA. And that is given by Q by epsilon naught, where this area is the A is the area of the plates of the capacitor. So this is given by A. And the change in electric flux is given by this expression d phi E by dt equal to 1 by epsilon dq by dt, and that can be written as dq by dt equal to epsilon naught d phi E by dt. Therefore, ID that's given by the displacement current is given by epsilon naught d phi E by dt. For this dq by dt, that's the displacement current or Maxwell's displacement current. Now, how to define the displacement current? The displacement current can be defined as the current which comes into play in the region in which the electric field or the electric flux is changing with time. In other words, whenever the change in electric field takes place, displacement current is produced. So Maxwell modified Ampere's law as line integral of b dot dl equal to mu naught I, and that's equal to mu naught into IC plus ID, the total current, conduction current, and the displacement current. And line integral of beta dl equal to mu naught IC plus mu naught epsilon naught d phi e by dt. So this total current enclosed by the surface becomes the sum of the conduction current and the displacement current. That's given by E equal to IC plus ID. And this equation 5.6 is also known as Ampere-Maxwell law. When the current in the circuit is constant, the displacement current is 0. Between the plates, the conduction current is 0 while the displacement current is not 0. This displacement current or time varying electric field can also produce a magnetic field between the plates of a capacitor. The magnetic field at a point inside the capacitor is perpendicular to the electric field, and that is shown in 5.6. This magnetic field can be determined by using the equation 5.6. Yeah. Now, what is the importance of Maxwell's correction? The importance of Maxwell's correction is given like this. We know that the Earth receives radiations from the Sun and other stars. These radiations travel through empty space where there are no electric charges and hence no electric current. Ampere's law says that only electric current can produce a magnetic field. If Ampere's law alone is true, there will not be any radiation at all. Maxwell has introduced a correction term given by mu naught epsilon naught d phi e by dt. Ampere's law ensures that the time varying electric field or displacement current can also produce a magnetic field. Though conduction current is 0 in an empty space, the displacement current does exist. So the equation 5.6 becomes line integral beta dl equal to mu naught epsilon naught d phi e by dt. In stars, due to thermal excitation of atoms, time varying electric field is produced, which in turn produces time varying magnetic field. According to Faraday's law, this time varying magnetic field produces again time varying electric field, and so on. The coupled time varying electric and magnetic fields travel through empty space with the speed of light and is called electromagnetic wave. Even though Maxwell initially started with purely symmetry argument, his correction term explains one of the important aspects of the universe, namely the existence of electromagnetic waves. Now, why this is called as displacement current? The name stuck because Maxwell named it. The word displacement is poorly chosen because nothing is being displaced here.
Electromagnetic EM waves, focusing on the limitations of Ampere's circuital law and Maxwell's landmark correction. Displacement current Maxwell identified an inconsistency in Ampere's law when applied to a charging capacitor. He proposed that a changing electric field between the plates of a capacitor acts as a current, which he termed displacement current. This current completes the circuit even where no physical conduction occurs. Maxwell's equations. Maxwell unified electricity, magnetism, and light through four fundamental equations. Gauss's law, electricity, relates net electric flux to enclosed charge. Gauss's law, magnetism, states that magnetic monopoles do not exist. Magnetic field lines form closed loops. Faraday's law relates a changing magnetic flux to an induced electric field. Ampere-Maxwell law states that magnetic fields are produced by both conduction current and displacement current. Significance. These equations predict the existence of electromagnetic waves, which propagate through vacuum at the speed of light. 10 multiple-choice questions, MCQs. What was the inconsistency Maxwell found in Ampere's circuital law? A. It only applied to static charges. B. It failed for time-varying electric fields, like charging a capacitor. C. It ignored the mass of electrons. D. It predicted light travels slower than. The displacement current is proportional to A. The rate of change of magnetic flux. B. The resistance of the wire. C. The rate of change of electric flux. D. The total charge on the plates. According to the Ampere-Maxwell law, a magnetic field can be produced by A. Conduction current only. B. Displacement current only. C. Neither conduction nor displacement current. D. Both conduction and displacement currents. Which Maxwell equation implies that magnetic monopoles do not exist? A. First, Gauss's law for electricity. B. Second, Gauss's law for magnetism. C. Third, Faraday's law. D. Fourth, Ampere-Maxwell law. The unit of displacement current is A. Volt, B. Weber, C. Ampere, D. Tesla. Maxwell's equations unified which of the following branches of physics? A. Mechanics and heat. B. Electricity, magnetism, and optics. C. Gravity and quantum mechanics. D. Thermodynamics and acoustics. In a vacuum, the speed of electromagnetic waves is determined by A mu 0 and epsilon 0. B. The frequency of the wave. C. The intensity of the light source. D. The temperature of the medium. The line integral of the electric field around a closed path is 0 if A. There is a changing magnetic field. B. The magnetic flux is constant or 0. C. The conduction current is maximum. D. The displacement current is 0. Who experimentally confirmed the existence of electromagnetic waves? A. James Clerk Maxwell. B. Michael Faraday. C. Heinrich Hertz. D. André-Marie Ampère. Gauss's law for electricity indicates that electric field lines A. Always form closed loops. B. Start at positive charges and end at negative charges. C. Are perpendicular to the magnetic field lines. D. Cannot exist in a vacuum. 10. 2-mark questions. Define displacement current. State Gauss's law for magnetism and its physical significance. Write down the integral form of the Ampère-Maxwell law. Why did Maxwell need to modify Ampere's circuital law? What is the significance of the first Maxwell equation, Gauss's law for electricity? How are electromagnetic waves produced according to Maxwell's theory? Give the mathematical expression for the speed of light in vacuum in terms of permeability and permittivity. What does the third Maxwell equation, Faraday's law, relate? Distinguish between conduction current and displacement current. What is the importance of Maxwell's equations in modern communication?